speaker, I asked for them to send me a bio. And usually they send me a couple well-crafted 3 or 4 sentences, sometimes a paragraph and a half. I'm not quite sure what to do about it. Dr. Lutman just sent me this list of fascinating things that he has done in his life and said, choose as many or as few as you'd like. So I'd like to share some highlights that I found entertaining, although we could spend a whole hour discussing the fabulousness of Dr. Lutman. Mathematically, he's been the associate editor of the Mathematical Monthly Problems section since the mid-1970s. There's this great section where they pose problems and then students send in answers. He's one of the guys that looks through the solutions to see if they're correct or not and if the questions are appropriate. He volunteers as a mathematics instructor at San Quentin Prison, which I think is fabulous volunteer work. He also has been the host of the War and Peace lecture series for a long, long time. I think you're turning the reins of that over to someone else this semester. But if you're a student here and you're unaware of that, go find it next semester and go participate. It's a fabulous lecture series. He's written 2 books on raising fowl. One is called Chickens in Your Backyard, and the other one's something about waterfowl, but he didn't give me a title. So if you need to raise chickens, again, he's the go-to guy. And he's done field research in Alaska on Eskimo dance. So welcome to fabulous and versified Dr. Lutman.
Thank you, Cora. By the way, the War and Peace lecture series is offered every fall term, and you're encouraged to take it. I know some of you already are. It's quite an important course, I think, and an important subject to look at. The subject I'm going to talk about today is the mathematics of apportionment. We offer a course here in the math department called Math 105, Math and Politics, where we deal with this issue among others. Many people are surprised to hear that there's a course in math and politics. What do they have to do with each other? But this will give you some idea of one of the topics that we discussed. So I put up here on the first screen the beginning of the Constitution. It starts out with the preamble. In my school we had to memorize that when I was a kid. But it certainly is very eloquent. But we'll skip that for now and get into the details. So it starts out with Article 1. The legislative branch, and it says the legislature is going to consist of a Senate and a House of Representatives. Well, you've probably been through this in your history. You know that we have a Senate where each state is represented equally with 2 senators, and we have a House of Representatives where the states are represented according to their population. And you probably remember that this was the result of a compromise between the large states and the small states. There was quite a big discrepancy between the sizes of the states back in the 1780s. As of the first census in 1790, Delaware was the smallest state. It had a population of just under 60,000, which makes it about equal to modern-day Petaluma. The largest state then was Virginia, with a population of just about 750,000, which is equivalent to modern-day San Francisco. So about 12.5 times bigger. Incidentally, Virginia then consisted of not only what it does today, but also West Virginia. When the Civil War began and Virginia decided to throw in with the Confederacy, the westernmost counties of Virginia said, well, we'd rather stay with the Union, so they broke off from Virginia and were granted statehood in 1862. But back in the 1780s, Virginia included all that as well. Incidentally, we're used to thinking of New York as being the most populous state in the East. In fact, up till about a half a century ago, New York was the most populous state. And in approximately 1960, California passed it up. You know, that's why it used to say on New York license plates, the Empire State. And now it just says one of the provinces. Doesn't it? So anyway, the small states argued, well, look, we're making a union of states here, so it really doesn't matter how big, how small. we're all states, we're all equal, we should have equal representation. Well, the larger states weren't having any of that. They said, look, we're making one nation, and we have more potential citizens of that nation than you do, so we should have more power in the legislature. So they compromised and they made two houses of Congress, one in which representation was by state and the other in which it was by population. So now there's a lot here about the Senate, which I didn't include because that's not our discussion for today, but here's the stuff that's in the Constitution about the House of Representatives. And the operative statement for our purposes is right here in italics, where it says representatives shall be apportioned among the several states according to their respective numbers. Now that's all it says about the apportionment. There's a lot of other stuff in here. They fuss about such things as, well, there's going to be an election every 2 years, and you have to be 25 years old and have been a citizen for 7 years, and a resident of the state you're representing. It doesn't say you have to represent in the congressional district you're representing, but that would be a matter for the states to decide. Also, who's going to be counted? It went into that, and right down in here it says that it's going to count free persons. Notice that persons is a gender neutral word, so they were going to count women, even though at that time women couldn't vote and were hardly citizens. And then what about Indians? Well, Indians who paid taxes were going to be counted. And then it says over here, 3/5 of all other persons. Who's that? Well, that's slaves. Yeah, they apparently didn't want to, too embarrassed to use the S word, but it's slaves. They're going to count at 3/5 of a person. This is one of the strangest political compromises in all of human history, I think. The southern slaveholding states were in kind of an awkward position because, well, they wanted as much power as they could get in the new government, so they were trying to argue that everybody should count. But it was pretty cynical to try to count slaves because they certainly weren't citizens and they were barely regarded as human. I mean, it was almost as though they had suggested counting horses as well as people. Meantime, in the North, where they didn't have slaves, their view was, no, we should count people who are actually citizens. So they compromised. How they got this 3/5, nobody knows, but they're at 6. So let's see, what else? Okay, there's going to be an enumeration, i.e. a census, every 10 years. And then they wanted to get started right away, so they didn't want to have to wait for the first census. So it says, up until we have a census, here's what's going to happen. New Hampshire gets 3, Massachusetts gets 8, Rhode Island and Providence Plantations gets 1, and so on. 65 altogether in the first Congress. Incidentally, Rhode Island and Providence Plantations is the full name of the state of Rhode Island. It's the smallest state with the longest name. So anyway, there's a lot of fuss in here about things, but it doesn't really say anything about exactly how the apportionment is to be done. And the only thing we can presume is that the Founding Fathers thought it was obvious. They probably never done it, so they just figured, it's clear, right? What is there to say? One other thing that isn't in here is anything about how big the House of Representatives was to be. Not even implicitly, except for right down here where it says, the number of representatives shall not exceed 1 for every 30,000. That in effect puts a maximum on the size of the House of Representatives, but it's become increasingly irrelevant as the nation has grown. Today we're about 300 million. That puts a cap of 10,000 on the House of Representatives. Can you imagine? 10,000 representatives. I mean, it's utter chaos the way it is, with about 4% of that number. So Congress has always felt entitled to set the size of the House itself. Well, let's actually look at what's involved here. So we'll look at the results of the first census. Now, by the time they got around to doing the first census, there were 2 more states that had been added to the original 13, Vermont and Kentucky. So over here is a list of the 15 states in alphabetical order. I've listed their populations as of that census, and down here's the total, which is just under 4 million. Here are the percentages, so I got those numbers by dividing each state's population by the total. Now, they had decided, for reasons that have not come down to us, that the first decade, the Congress was going to be 105. I don't know why. But we apply that percentage then against the 105, and we come out with these numbers, which are called the standard quota. And those are the numbers that represent the actual number of delegates each state should have if fractional delegates were allowed. Now, one could argue, well, why not? Send a delegation, there could be any number of people, but this is how many votes they get. Yeah, but that's clearly not what they meant. They wanted single representatives, and they wanted it to be whole numbers. So somehow we've got to get from this table to whole numbers. All right, well, sounds like a simple problem. You round off. The usual rule of rounding off is when the fractional part is less than half, as it is in this case, you round down. So Connecticut would be rounded down to 6. Here is Delaware, 1.594. That's bigger than half, so you round up to 2. Georgia's less than half, rounded down. Kentucky, look, almost 2, very, very close to 2, so it's rounded up to 2, and so on. Now, the trouble is this column of numbers adds up to exactly 105, even though these are not integers. This column, it's all integers, so of course the sum has to be whole numbers, but it's 106, not 105. Now, at first blush, it looks like, ooh, we must have made a mistake, something went wrong. No, actually we didn't. In fact, if there's any surprise here, it's that we got such a close number here to that one. I mean, look, when you round off, you're changing the numbers. And you're changing some of the numbers by making them bigger, and some are making them you're making smaller, and the amounts vary. So there would be no reason to expect that this column of numbers would add up to the same as this one. In fact, just by luck of the draw, it could have been that all 15 of these numbers had fractional parts that were less than half, and then you'd round them all down. Or vice versa, they could all have been bigger than a half, and you'd round them all up. Those are rather extreme cases, but the point is that could happen. So we're kind of lucky that we got even this close. Well, Alexander Hamilton is the first person who is going to play a role in our story here. I'm going to put this one on the other screen in case we need to refer to it. So Alexander Hamilton is a name you probably know. He was one of the founding fathers, one of the signers of the Declaration of Independence, one of the authors of the Federalist Papers, which was a public discussion of the whole theory of government. And I'll bet a lot of you probably have a portrait of Alexander Hamilton in your pockets. His picture is on the $10 bill. And there's a very nice engraving of the U.S. Treasury building on the back side, in honor of the fact that Alexander Hamilton was actually the first Secretary of the Treasury in President Washington's cabinet. Alexander Hamilton never became president, largely because he was killed in a duel with Aaron Burr before it was his turn. Hamilton had this idea. Instead of fixating on that 0.5 as the dividing line between rounding up and down, let's change that. Let's imagine changing it. For instance, maybe we'd make it 0.6. So the fractional part is bigger than 0.6, we'll round up. If it's less, we'll round down. And in fact, that works in this case because it turns out that let's look over here, the only one of these numbers that has a fractional part between 0.5 and 0.6 is Delaware's. Well, that's the only one that would change if you change the rule. Delaware would be rounded down then because it's less than 0.6 instead of rounding up. And that's great because we've got one to get rid of here. We gave away one too many seats. Now, to be honest, that's the way I just described it is not the way Alexander Hamilton described it. It amounts to the same thing, but here's what he said. He said, let's tentatively award each state the integer part of its quota. We could say rounding down, but that's essentially picking the integer part. And that will give away a certain number of seats, and then, but not all of them. And so we'll have some left over, the excess seats, and we'll award them to the states in order of priority. And the priority will be the higher the fractional part, the more they're entitled to it. So what I've done here is I've listed the same 15 states with the same populations and the same shares of the 105 seats, but I've scrambled the order now. They're not in alphabetical order. They're in order of descending fractional parts. So you have Kentucky up here with 0.987, and it's the biggest, and 0.965 for New Jersey, and so on all the way down to Virginia at 0.158. So we take the integer parts, those are here, and that adds up to 96. So we're giving away the 96 seats. So we have 9 more to go. And so what we'll do is go down the list through the first 9 and give them each an additional seat. So there's 1 for Kentucky's integer part, but adding 1 because it's the highest on the list gives it 2, and so on. And we go down through here. Maryland gets the 9th one. Delaware would have been next, but there weren't enough. So that's the way Alexander Hamilton proposed to do this. Well, Congress said, that sounds like a good idea. So they passed a bill saying this is how we'd like to do it, and they sent it to President Washington, who promptly vetoed it. It was the first veto in our young republic's history. And Congress did not have the 2/3 votes to override it, so they were dead in the water. Now, Washington did send a veto message over to Congress. It was a little vague, but it seems like what bothered him about Alexander Hamilton's method was that the states weren't treated the same. Some of them were rounded up and some were rounded down, and in fact, the division line was rather arbitrary. It wasn't going to be the same every time. So, enter on the scene Thomas Jefferson. Now, some of you might have a portrait of Thomas Jefferson in your wallet, but it's less likely. He's on the $2 bill. Don't see many of those. On the back side of the $2 bill, on the green side, is a nice engraving of Monticello, which was Jefferson's estate near Charlottesburg, Virginia. Now, Jefferson, of course, was also a very important one of our founding fathers, not only a signer, but in fact the author of the Declaration of Independence, and of course eventually became president. He was our 3rd president, elected in 1800 and again in 1804. He was actually the Secretary of State in George Washington's cabinet. So he had another idea, and I will explain that to you now. But first we have to think a little bit more carefully about what we did over here. to get the so-called standard quota, these numbers here, remember what we did. We took each population, we divided it by the total, and then we applied that against the size of the house. So I just wrote that in algebraic terms here. SQ for standard quota is the population of the nth state divided by the total population, which gives you the fraction of the population, and I took that fraction of what I'm calling H here, which is the desired size of the house. Now, through the miracle of algebra, that is equivalent to this statement here. I've rearranged things so that we divide the H by the T, you see, and then multiply that by the PNs. Totally equivalent, but the difference is that this is somewhat easier to use for the simple reason that you have to do only one division. You divide H by T, and that's once, and then you just simply multiply that by the various P's, the populations. Whereas up here, you have to do all these divisions of Pn by T over and over again, and then each quotient is multiplied by H. Yet another way to write this formula is here, where instead of multiplying by H over T, I divided by T over H. Now, it's algebraically equivalent, but you might say that's a rather peculiar, if not perverse, way to write the expression. I've still got one division to do, T by H, as I did here, H by T. But now I'm dividing into the PNs instead of multiplying by the PNs. And division's a little messier to do, a little harder than multiplication. Why are we complicating things? Well, there is a reason, and that is that we can give an intuitive meaning to TH, T over H, that is not so clear about H over T. What is T over H? What happens when you divide the total population of the country by the number of seats in the House?
How much does each seat represent in the population?
Yeah, it's the number of citizens that are represented on the average by each member of the House. Or to put it another way, it's the average size of a congressional district. In 1790, that was about 37,000 people. Today, it's more like around 600,000. But it's a number we can relate to. Whereas its reciprocal, very, very tiny number. It starts out with a bunch of zeros. It's not as intuitively clear. And that's really the only reason for writing it this way instead of that way. Anyway, Jefferson's idea was to tinker with this denominator, this divisor down here. Tinker with the average size of a congressional district. It was only an average, after all. So what he was thinking is, let's change that. If we make it smaller as a divisor, then the quotients will be larger. And if we take the integer parts of those modified quotas, we'll have tentative assignments of House seats, and we just keep doing that, as it were, reducing the size of the House, increasing the modified quotas until the integer parts add up to 105, which is what we want. Now, tinkering with the divisor, however, whatever you may think of it, turns out to be common to methods of apportionment. We're going to look at several others today. All of them except Hamilton's do that. In the case of the 1790 census, T is this number here, a little under 4 million. That's the same number that we had over here. H was set at 105, so the quotient is 37,085. That would be the average size of a congressional district. Jefferson modified it to 35,000, and this turned out to work. Behold, here's what I've done. Here's again the list of the 15 states, back in alphabetical order, their populations. What I've done now, though, is I've divided the populations by 35,000. That's what we did on that in the previous page. That was what the formula said to do. And what that gives us is the number of districts of size 35,000 that would fit in each state. And of course, it won't come out as a whole number, generally, but there they are. And what we're going to do is take the integer part of these. That was Jefferson's plan. Take the integer part, but of slightly larger numbers than we had before. And so here they are. And that was Jefferson's plan for apportionment. Notice that though it's conceptually quite different from Hamilton's method, it winds up assigning just about the same number of seats to each state. The only differences are these two that I've marked with an asterisk. Rhode Island gets 1 seat instead of 2 under Jefferson's method, and Virginia gets 21 instead of 20. Now, why do you suppose Washington and Jefferson like this method?
Yeah, Virginia, just.
They're Virginians, yes. Could that have something to do with it? We were just talking about the fact that Jefferson's estate, Monticello, is near Charlottesburg, Virginia. Thomas Jefferson was a Virginian. George Washington's estate was Mount Vernon. That's also in Virginia. Washington was a Virginian. Maybe they had a slight bias in favor of Virginia. On the other hand, perhaps they were noble statesmen who wouldn't stoop so low. Hard to tell. But it's not actually a coincidence that Virginia gained a seat here. Jefferson's method intrinsically favors larger states because this idea of reducing that divisor and therefore increasing the standard quotas is going to increase all of the standard quotas by the same factor. But when you increase a bunch of things by the same factor, the bigger ones grow by more than the smaller ones. It's sort of like, we're all used to paying sales tax, right? At a fixed percentage. Say it's approximately 8%. Yes, but 8% on a $20,000 automobile, $1,600, is going to be a lot more than 8% of, say, a $200 microwave. It would be $16. So the standard quotas are going to be increased more for the higher states. And they have a better chance of crossing over a boundary into the next integer interval. Now, one other thing I want to mention here. Jefferson made it sound as though this all had to be done by trial and error. You took a guess about this number, 35,000. If it worked, that's great. If not, well, it should be clear from how far off you were and which direction you were off, whether you needed to go farther or you'd gone too far. But actually, it's not necessary to do it by trial and error. Think about it this way. Remember when we were looking at that first table, our initial thought was just to round everything down and see what happens. And we had too few seats then, only 96. So imagine that you gradually reduce that divisor, the average number of House seats, and gradually raise the standard quotas. And every now and then, one state will reach an integer point and will cross over that boundary, and the integer part will change, and then we'll get an extra seat. And you gradually do this, and one at a time the states cross over that boundary until you've gotten rid of 9 seats, and then you stop. Well, we don't have to be so passive about it. We could figure out how much we have to increase these standard quotas by to get them to cross to the next integer. So look at this one, this table. So what I've done here is, here's the same data that we've seen several times before. 15 states in the alphabetical order, their populations, their standard quotas, the share of 105 seats. In the case of Connecticut, the next higher integer is 7. By what factor do we have to increase 6.408 to get to 7? Well, that's easy enough. You just divide the 7 by the 6.408. I did that. That's right over here. In other words, you have to increase this about 9% to get it to move across the next integer boundary. With Kentucky, remember it was 1.987, almost 2. So you don't have to increase it by very much to get the next integer. Just, about 2/3 of 1% is all it takes. And New Jersey down here was also pretty close. Takes just slightly more, 0.0070% increase, 0.7% increase, and it will cross over to the next boundary. So now Massachusetts, for example, is pretty close to 13 numerically, but it still takes 1.5% almost to increase it to 13. Well, what I did was I looked at all these factors that you have to increase by to get it to go over the boundary to the next number. And I ranked them in order. This is their rank order. Number 1, Kentucky, that's the smallest number. Number 2, New Jersey is the next one. 3 is Massachusetts, and so on. And I said, well, we got to get 9 of them to do this, to go over the next boundary, but not 10. Well, number 9 is right here. The factor is about 4.5%, and number 10 is down here. It's a little over 7%. So if you just pick any percentage in between, that should do it. Oh, there is, by the way, a slight chance that while you're trying to get that last state up over the integer boundary, one of the ones that you had already gotten over an integer boundary might go over another one. Yes, that could happen. But don't worry too much about that, because first of all, it'll be pretty obvious when that happens, and secondly, it's easy to fix. So you just, if you saw that by going to 9, one state had actually gained 2, you'd say, okay, fine, let's back off to 8 states instead of 9. So we can pick something convenient in between. 1.05 is in between, or better yet, since we're worried about dividing, we could divide by 0.95, which gives us 1.05263. In other words, reduce the average house district by 5% from 37,085 to 35,230. That would work. Jefferson's figure of 35,000 worked because that's a reduction of 5.632%, or as a decimal 0.05632. We're reducing by that much from 1, and we're using it as a denominator. So in effect, we're increasing everything by just under 6%. Now, this is sort of an aside, but the point is that you don't have to guess. You can do it by a rather systematic method. So that was Jefferson's idea, and having nothing better to do, the Congress passed it in 1794, and that was how the apportionment was done for the decade of the 1790s. And Jefferson's method was used again in 1800, and in 1810, and in 1820. In 1820, something strange happened. Now, you'll notice that with Hamilton's method, which was just rounding a standard quota up to the next integer or down to the next lower integer, it would never go to anything but those two numbers, the nearest two numbers. Any system that has that property is said to, quote, meet quota. If an apportionment system makes an assignment that's not one of those two integers, it's said to violate quota. Well, in 1820, they discovered, although they didn't have a name for it yet, because they never thought that this could happen, they discovered that Jefferson's method violated quota. It happened with respect to New York. New York's population in the 1820 census was this number, almost 1.4 million. That's about 15.25% of the whole population of the country, which by then had gone up to almost 9 million. They had decided to have 213 seats in the House that decade. So New York's standard quota was 213 times 15.26%, which is 32.503. That was its standard quota, and any system that met quota would have assigned New York either 32 or 33 seats. But the modified divisor that year was set at 39,900, reduced from the original standard divisor, 42,112. So New York's quota was changed to 34.305, and when you round down or take the integer part, it got 34 seats, not 32 or 33. Well, as I say, it was a total surprise. Nobody had ever thought this would happen. And they just wrote it off at the time as a fluke, an anomaly. Let's hope it never happens again. But in the 1830 census, it did happen again, and it happened again with respect to New York, in fact. New York's standard quota was 38.59, but under Jefferson's method, it was assigned 40 seats. And it turns out, so much was this not a fluke, that if Jefferson's method had continued to be used to apportion seats in the House, it would have violated quota in every census from 1850 on. In fact, every census from 1820 on, except coincidentally for the one of 1840. So it's intrinsic in the nature of Jefferson's method that it's very, very likely to violate quota. Now, what had passed as an acceptable fluke in 1820 got everybody really upset in 1830, especially Daniel Webster. Now, you won't find his portrait on any of your money, and he was never a president, but he was a very powerful and important political figure in his era. He was a member of Congress, an important leader, a great orator. He threw a fit about this. He said, this is not only unethical, but it's a violation of the Constitution. We are not fulfilling the intent of the Constitution if we allow a violation of quota like this. So they decided they needed some new methods. John Quincy Adams came up with one. Now, John Quincy Adams was the son of John Adams, who had been our second president. Quincy Adams himself served a term as president. He was a one-term president in the 1820s. He suggested a method, but it turns out it was sort of an upside-down version of Jefferson's. Jefferson's method was always to round the modified quotas down, but you get the right numbers by elevating the numbers that you're rounding down. John Quincy Adams said, why don't we round up, and that'll give away too many seats, but then we'll push these standard quotas down, and until we've got the right number. Well, I think everybody pretty much recognized that Adams' method was just the sort of the mirror image of Jefferson's, and it was going to have the same problems. So Adams' method was never used. The chief difference between Jefferson's and Adams' method is, I've already argued that Jefferson's method was favorable to the larger states. Adams' method was favorable to the smaller states, because now you're forcing these modified quotas down, all by the same factor. You're going to bring big numbers down by more, and they are more likely to cross an integer boundary, and the state will lose a seat. But Daniel Webster himself came up with an idea. It was sort of halfway between Jefferson and Adams. He was still going to tinker with the divisor, that average size of the congressional district, to force the standard quotas up or down. But rather than round down, as Jefferson did, or round up, as Adams did, he was going to round off. Go back to the original idea that on the first slide here. You round up if the fractional part is bigger than 0.5, and down if it's less. But the numbers that you're doing that to are not the original numbers, or the modified numbers brought about by tinkering with the average size of the house. So I've shown you on this slide the same information we had before, but I've expanded these now to some more columns, and we can see what would have happened to that original, in that original decade with Adams' method and Webster's method. By the way, I'm applying everything to that original census, even though historically we've moved on now. First of all, so we can just compare apples to apples, and secondly, because it's the shortest list. Now, by the way, Webster's method could also violate quota in theory, but it's extremely unlikely. To get an example where Webster's method violates quota, you have to make something very bizarre, almost perverse. And in fact, if Webster's method had been used consistently up to the very latest census in 2000, it would yet, in fact, if you had used it from 1790 on to the most recent census, it never yet would have violated quota. Well, so Webster's method was used in 1830 and again in 1840. In 1850, a congressman whose name was Samuel Vinton came up with what he thought was a brand new, exciting way to do the apportionment. It turned out it was essentially Hamilton's method, but he didn't realize that, and apparently nobody else noticed it either. So, and it turned out it was used for the rest of the 19th century, and it was called Vinton's method. But I'm going to continue to refer to it today as Hamilton's method, because I don't want to confuse you about it. It was really the same as Hamilton's. But Congress, anyway, liked it. So in 1850, they adopted Vinton's method, i.e. Hamilton's method. And in fact, they even passed a law that said this is how it should be done in the future. And it was done that way in 1850, 1860, 1880, and 1890. Not in 1870. 1870 was a real disaster. It was a real low point in our political history. They did the apportionment that year by just political horse trading. No system at all. It was just, let's dicker with each other until we got something that a majority will pass. So it was not only a violation of the Constitution, but it was also a violation of Congress's own law from 20 years before. And it had a very serious consequence in 1876 when there was a presidential election. Rutherford Hayes of Ohio was running against Samuel Tilden of New York. Tilden won the popular vote. The Electoral College, however, turned into a complete disaster. There were, in the instance of several states, there were multiple delegations from the states that showed up, each claiming to be authorized to vote that state's electoral responsibilities. There were people who were not qualified to be electors and so on. Very chaotic. Congress decided to create a commission to settle the matter, and they decided they'd pick Supreme Court justices to do it because, well, justices are supposed to be, even-tempered and so on. Of course, we tried that in 2000, and look what happened. Gore versus Bush went to the Supreme Court, and they all had their ideological biases, and that's exactly how they voted. That's presumably what happened in 1876, and it turned out that the leading power, the leading party was Rutherford Hayes' party, and so eventually all the electoral votes that were in question were given to him, and so he became president instead of Tilden. None of that would have happened if they'd done the apportionment right in 1870, because it wouldn't have even been close. All right, the next thing I want to talk about is some problems that began to develop with Hamilton's method. It became apparent over about a 20, 30-year period, starting in 1880, that there were paradoxes that arose from Hamilton's method. The first one that was discovered is called the Alabama paradox. In 1880, Congress asked the Census Bureau to show it what the apportionment would have been by Hamilton's method for all possible house sizes between 275 and 350. Now what one would have expected to happen is, as you look down this table, each time the house is increased by one state gets an extra representative and everybody else stays the same. But it turned out that going from 299 to 300, 2 states increased their representatives and one lost one, and that one state was Alabama. So this is known as the Alabama paradox. I want to stress, by the way, that this is all theoretical. I mean, Alabama did not actually lose a seat, because they were just experimenting with what the theoretical possibilities were. But you can see from right in the middle here what went wrong. It's Hamilton's method. There's Alabama's standard quota. There's Texas's. There's Illinois'. We're looking at the fractional parts. 646 ranked Alabama 20th. To 3 decimal places, Texas and Illinois are tied for 21st and 22nd. It turns out there were 20 to give away. Remember Hamilton, you take the integer part and then you have too few, so you give away the rest of the seats in descending order of integer part. When they went to 300, now that's a very slight change. You're not changing any populations. All you're doing is multiplying the population percentages by 300 now instead of 299. The numbers are going to get bigger by the factor 300 divided by 299. In other words, they're going to get 299 bigger. That's not very much, and indeed, look, that number is very slightly bigger than that, this one than that, this one than that. But again, like with the 8% tax, when you apply that increase to the bigger number, you get a bigger increase. This is an increase of 0.062, this is an increase of 0.032, and this of 0.025. Well, none of the other states changed their orders, but now Illinois has broken its tie with Texas, and Texas has slightly beaten out Alabama. I'm looking at the fractional parts here now. So Illinois is 20th, Texas is 21st, Alabama is 22nd. So everybody gets their integer part, and there were 20 excess seats before, but now we increased the House by 1, so there's 21. And so Illinois gets 1, and Texas gets the last one, and Alabama doesn't. So, under the at 299, Alabama got 8, Texas 9, Illinois 18, but at 300, Alabama 7, Texas 10, Illinois 19. That's the Alabama paradox. Subsequently, 2 further paradoxes were discovered. One is called the population paradox. You know, if a state's population increases from one census to another, that doesn't guarantee it any more seats, because everybody's might have increased, probably did. But you'd figure if one state's population increased by a higher percentage than another, then it would have a greater claim, as it were, to gaining a seat. Well, from 1890 census to 1900s, Virginia lost a seat to Maine, even though Virginia's population grew by a larger percentage than Maine's. So that's called the population paradox. And there's also a new states paradox. I'll just very briefly say that the problem here they discovered when they admitted Oklahoma in 1907 as the 47th state. They simply increased the size of the House by 5 and gave those representatives to Oklahoma because that was how much its population would have entitled it to. But then somebody discovered that if you'd started de novo with the additional 5 seats, Oklahoma still would have gotten 5, but New York would have lost a seat to Maine. Oh, I skipped over this paragraph. This is just to say the Alabama paradox was repeated in spades in 1900 when there were several instances where as the population, as the house size went up by 1, a state lost a seat. In fact, from 356 to 357, 2 states, Maine and Colorado, both lost a seat. 3 of them gained. And oddly enough, except for Colorado's presence there, Maine is the one that lost the seat in all the other cases. It's rather a coincidence that it was that same state. Okay, we're almost done here. Because of all these problems with Hamilton's method, Congress decided in 1900 to abandon it, and it's never been used again. Webster's method was used in 1900. By 1910, a new method had been proposed called the Hill method, and that is actually, it's an important one to discuss because it's the one we're using today. I should mention, however, also that in 1912, when Arizona and New Mexico were admitted as the 47th and 48th states, Congress decided to fix the size of the House at 435. And that's still what it is today. So it's been the same for 100 years. And the only additional states that have joined the nation since then were Alaska and Hawaii, almost at the same time, about 1959. They're rather small states. Alaska to this day still has only 1 congressman. I think Hawaii might have 2 or possibly 3. They're small. But anyway, so Hill's method was proposed. Who's Hill? Well, Hill was the chief statistician with the Bureau of the Census, and he was supported by a mathematician named Edward Huntington, who had looked into these matters mathematically. And but there was another mathematician named William Warren who argued vociferously and apparently very eloquently in favor of Webster's method. So Congress stuck with Webster's method in 1910. In 1920, we had another kind of low point in our political history. There was a big fight about whether to use Webster's or Hill's method, and it made quite a difference because there were several states which would have had a different allocation under the 2 methods. And they reached a stalemate. They couldn't come to an agreement, so they simply did nothing. They left things the way they were, which again is a violation of the Constitution. It says you take a census every 10 years and you reapportion. In 1930, a commission of the National Academy of Sciences was created to study the matter and recommended the Hill method. But it turned out that that year, the Hill method and the Webster method produced identical apportionments. So everybody could claim victory. In 1940,